It's not good. Okay, but I've only recapped, so the recording is not going to miss much. But perhaps this is a good point to ask if there were any questions. I think I've kind of just repeated basically what I said in everything except for the last 10 minutes yesterday. Is this clear so far, or are there issues that should be discussed? Okay. Okay, so it doesn't seem to be the case. Then let me now just go back into the last slides that I showed you yesterday, because they are really the core of what I want to bring across in this in these lectures, and it would be a bit of a shame if they were kind of too rushed and you missed this key point. So let me just go back. So this is a slide that I had already shown you yesterday, but I would like to just show you that again. So the idea, of course, of all the setup and the reason why I set it up in the way that I set it up was that I can now generalize this, and in particular I can add additional elements into the local description of my objects. Yesterday, of course, I had this local Taylor expansion that they used to build this local description of the product. But I'm free to add in extra bits as long as they satisfy essentially the correct axioms. So as long as they have order bound and change of base point formula. And I'm going to show you this again now, how this works on the level of this PAM as PDE. So this was the equation we wanted to solve, and the main point, or the main difficulty I wanted to address with this whole analysis was that I didn't know how to control this product here on small scales. And so the first step in now guessing what a good description of this sigma of u could be, in order to then construct the local description of the product, which I can then check the coherence of that it has the right continuity condition in the base point. So the first thing was just this naive guess, this freezing of coefficient type argument, where you would just replace in this equation here this variable, this varying u of z. If I want to have a base point, if I want to just understand how the solution u should look, or how it should fluctuate near a given base point, it's probably a good idea, very similarly to actually what we had done yesterday, to just replace the first order guess would be to just replace this by a constant function on a ball, right? And so we would then guess that at least near that base point z0, it's a good idea. It's probably a good guess that this u is locally approximated by just the heat equation with a constant coefficient here. But then this is just a parameter. So this is of course then linear in the right hand side. So that suggests what I have written here, that to leading order near the base point z0, my increments of u are just given by here this constant, and by this number now, times the increment of the constant coefficient equation, which is here just this stochastic heat equation. Okay, so this is very much, I've tried to make this slide look very similar to the slide that I had shown you in the first lecture about the derivation of the local expansion for rough path. So I hope you see the similarity. And another similarity is, of course, that in the rough path case, we had the increment of Brownian motion here. So except for that, the argument was identical. But here this is a very similar object, because it's the solution of a linear equation with a Gaussian right hand side. So in particular, this z itself is going to be a Gaussian process, and I will show you a little bit later that we know everything about it. Just like pretty much just like for Brownian motion, we can really get our hands very explicitly on this object. It's very explicit. So that's good. So this is our first order guess what the expansion should look like, and now we can use this to improve on our expansion, on our local expansion of this thing. So here, of course, I've committed an error by replacing it by the constant. So I'm just putting the next order term, which was just one term in the Taylor expansion. So I put the derivative here, and then I have the increment of u, which again, this is exactly the same as what I had done in the rough path case. So you should, I hope you will feel this is really, I hope you will see the similarity. And then in here, I just plug in this guess that I had before. And that suggests that the next order in the expansion in the local description of this of the sigma of u, so to first order, I should have that. And to second order, I should have this, where I have now replaced the increment of u by this postulated increment of the z. Okay, so I hope it seems sensible. This suggests now, if I want to take the product with eta, well, what you should do is you should just take this this constant coefficient thing with multiply it with eta, and then you should take this thing, which again here, this is just a number. This depends on z, so it kind of goes in front, and then you have here the z increment tested against with eta, right? So I showed you the slide again, but I want to just really drill home on the fact that I mean, it looks, I hope you all see that this looks very similar to what we had done in the rough path case. And the slide is for me like really important, and it's sort of such a conceptual thing that I want to really make sure that everybody understands this. Just also, I mean, this is also something which is important, and the structure of the local expansion that one guesses here is very similar again to what we had already both in the rough path case and both in the Taylor polynomial case. So we had sort of a function here which depends on the base point, and then this was multiplied. Okay, here which is with the distribution. This is here a random object, but a Gaussian random object. And then here we have again a function of the kind of a coefficient in the expansion, and then this is again sort of, I mean, it's a polynomial in the Gaussian. Okay, so it's a very explicit thing. So it's very similar to what we had done yesterday in the first lecture for the Gobinet, for the definition of the rough path, where we had sort of taken here our path and then multiplied it with a Gaussian increment, the Brownian motion, and then the next order thing was again kind of a non-trivial path, this Gobinelli derivative, and then multiplied with this second order polynomial in the Gaussian, so this iterated integral. Okay. So I hope you see the similarity. And now what I want to, just like in the rough path case, I want to say, well, what do we actually need to do? So we have exactly, just as in the rough path case, we have the problem that this object, we have to define it, right? So this is on the next slide. The input for making sense of this thing is, of course, here. This is just the solution of this heat equation. And we had already seen, and I had argued very rapidly yesterday, that this in this parabolic sense should be an object of regularity just below 1. So this is, I mean, this is a nice object. But here this eta is of all regularity -1 so this here just about fails to satisfy our, I mean, the condition that the sum of these things is positive. And again, this is really an analogy to the rough integration, which I had showed you in the first lecture. So there it was the same, that we wanted to define this integral of w against dw. And again, kind of classical deterministic arguments didn't give me that, but so I just postulate what this thing should be. And I want to do exactly the same thing here as well. But before I do that, let me just introduce some notation. So I'm just going to call this thing with this symbol, which, okay, admittedly looks a bit odd. For now, just don't worry so much about it. I mean, this is a bit reminiscent of in regularity structures. You can go much further. You can introduce many more objects in your description, and then at some point just labeling them by letters becomes a bit of a mess. So one starts to label them by graphs, because one kind of can read off the graph what one has. And so this graph here denotes the fact that you have a noise which is solved with, then you solve the heat equation with that's this line, and then you multiply with the heat equation again. But okay, so that if you don't want to think about this, is just a symbol, and I just want to use it as a shorthand, and I use it in the formulas here in order to not have to write this long expression all the time. Okay. So we want for this object here, just as I had already announced, we want, just as before, again the same kind of properties as we had already seen before. So we want to have an order bound, and it's very important. So just in this formal derivation that I showed you yesterday, it's just on the previous slide, it's very natural that you have here this base point dependence, right? And so what you would hope here is, of course, this, if you view it as a running variable of the function eta, I mean, just as a function, this eta here will be a random distribution of regularity -1. So as a global object, this thing is not going to be better than regularity -1. But the hope is that if you just test it near that base point here, then you can harvest some extra smallness from the fact that this prefactor is small near that point. And then you can hope that in this particular, around this particular base point, you get a bound of order 0 minus, okay? So this is exactly, so the -1 is here, which is the regularity of the eta, but you can hope that you harvest an extra 1, which then puts it to 0 minus. And again, this is an analogy to what we have in the rough path case, where we had that this integral of s to t, the delta WR SR dWR was also typically of order t minus s to the 2 alpha, right? Because we have here this recentering. So it's really very similar. And then again, we have this change of base point formula, which of course, if you look at what this is supposed to represent, is really not complicated at all. Here's the only base point dependence. And so if I want to go from one base point to the next, I just have to put this extra term which corrects for it, okay? So that's certainly a sensible thing to postulate. And again, just like in the rough path case where you had this chance identity, which was a change of base point formula, it's not something which is complicated to guess. It's very natural to postulate that this should hold, right? And just a piece of vocabulary. So in Martin's theory, this is this object. So generally, the set of these kind of objects comprise what makes the model. So this is model is just the word that he uses for these kind of objects. So the model contains all this. All sorts of objects like that, and possibly if you do higher order expansion, it contains more. Is this clear about the stochastic data that I want to, for now, just postulate that I have it? And then I will later in this lecture go about actually constructing it. But for now, I want to just show you, argue with you that that if you have this and then have also the right objects to multiply them with, then we can actually define and control these products. So, and again, just an analogy to what we had seen in the rough path case. So there we had seen, we have now these rough paths. So we have essentially given a sensible meaning or a minimal set of properties that we want for this iterated integral of Brownian motion against itself to satisfy. And the second question was then which kind of objects can we integrate against that? And this meant that we had these controlled path, right? So this meant that locally the increments should look like the W. And we have exactly the same thing here. And this is the slide. It looks a bit longer, but I hope it's not so much more complicated. So perhaps don't read so much text. So the key identity is what I want. So I'm going to call these objects model distributions now instead of calling them controlled paths. So, but okay, that's just a different word, sort of for a similar concept. So the idea is I want to look at increments of this function u, so which now depends on various variables, and I want to leading order, just like with the controlled path, that this looks like the increments look like if you want a modulation. So you have this function. It's really in the analogy to the Gubinelli derivative. It should look like the increment of the z, right? So that's, and if you go back to the derivation that I had shown you in the previous slide, so you should really think of this mu of z to be the sigma of u of z naught. Okay, so that's I hope very natural, and I hope you find it directly analogous to what we had seen in rough path. The second condition, so let me walk you through that, is that of course we need some regularity control also on this, if you want, this Gubinelli derivative. And again, that's very much an analogy to what we had done in the rough path case, where you see that also in the proof of the Sewing lemma, we had used very strongly that we control the C alpha norm of this derivative, and it's exactly the same thing here. And the interesting thing is that the regularity bound that we need here is, right here we ultimately, let me just ignore this term for now. Here we ultimately want to have a bound of order gamma, and gamma is, say, it has to be bigger than 1. Here we then want to have a bound which is exactly a gamma minus the order of this object. Okay, so that's just the correct assumption that happens. It's very much similar to what you have in rough path, where on this kind of the 0 level you have a bound of order 2 alpha, and then on this next level you have a bound of order alpha. So it's really analogous to that. There is one thing here which doesn't really have an analogy in rough path, which is that we actually have to put this derivative. So let me just say, I mean, this is perhaps a bit of an odd notation, and this is just, if you want, the x component. So if z is equal to, this is a space-time point, so if that of x of t and z naught is equal to, say, x naught and t naught, then this is just the spatial component. Okay. So what you need here is, I mean, this is something that that is also possibly plausible that you have to put this. So yesterday we had seen, if we want to go to a level of regularity, if we want to harvest a regularity of order bigger than 1, even for a regular function, we have to put the derivative in the local description of this object if we want to do this calculation, very this coherence property. So we needed to put the derivative. That was the calculation I had shown you yesterday. And it's the same thing here. So we will ultimately need to understand what this u looks like to an order bigger than 1. So this gamma has to be bigger than 1. And that's just because we want to multiply the u with the eta, and the eta is of regularity below -1, just below -1. So we need to understand what u looks like to order bigger than but to an order to a strictly bigger than 1 order. And then it's probably plausible that, just like we had seen yesterday in the case of just multiplying function distribution, you had to put a derivative if you want to go above 1 derivative. And here you only need to put the spatial coordinates because of this different role that time and space play in parabolic counting. So sort of 1 derivative in time would correspond to 2 degrees of regularity. And so you don't only need to put the spatial. And then you, of course, want to put exactly the same kind of continuity condition on this if you want this generalized derivative, which is again similar to what we had done yesterday. So perhaps again, let me take a breath, because I think this is quite a bit to take in. Is this all clear? Or if you do me a favor, if you interrupt me and ask me a question.
Maybe a quick question.
Please.
So like back to the PAM more or less. So basically, yes. First,
go to another slide.
It's not really necessary, but it's more to the application back there. So first you basically fix your gem, and your gem basically tells you then how this Z, which I use then as my control, should look like.
Sorry, I haven't understood this. So I mean, yeah, I need to know what Z looks like. Yes.
Yeah, but like if I understand, it's just if I understand it correctly. Because first I kind of fix my gem, like how I want my distribution to be approximated. Because there we chose this approximation, like, okay, we freeze it at 1 base point.
Yeah.
This freezing already told me the whole structure of Z, of how Z needs to look like. That Z needed to look like the solution of just the linear heat equation.
Yes.
Is this like, I mean, maybe my question is a bit stupid, but is this like a canonical choice always, how this Z should look like? Or
I mean, this idea that you have something that has sort of varying coefficients, and then you do a freezing of coefficient, and it allows you to compare things to sort of constant coefficient equations is very common in PDE. It's, I mean, if you know if you have, for example, seen just the proof of classical Chowder estimates, for example, in elliptic or parabolic regularity, it's very much the same. And in a sense, what you have to do there always is you compare the non-constant coefficient equation to a much more canonical constant coefficient equation. So in that sense, what we're saying is that the solution to this, with this non-trivial dependence on u on the right-hand side on small scales, should look like the much more canonical constant coefficient equation. Does that somewhat answer your question? Or
yeah, I think so. My question was maybe a bit unclear, but thanks.
But I mean, I think it's generally true for these for equations of this. I mean, I'm not showing you this for PAM, but I mean, the solution of the linear equation sort of pops out in basically all of these equations. I mean, the theory is very well geared to deal with equations where this Z pops up naturally. Perhaps that's the correct way of phrasing it.
Okay. So there is no question you know of where the Z would be given like as a solution of a nonlinear equation, of another nonlinear equation you understand better.
No. What does happen? I mean, this I won't have time to explore here, but there's some work that I also mentioned already that I've done a couple of years ago in collaboration with Felix Otto, and then later on also with Jonas Sauer and Scott Smith, where we kind of looked at a more complicated situation where we don't have a multiplicative, we don't only have a multiplicative noise on the right-hand side, but we actually have a quasi-linear operator. So the diffusion coefficient itself also depends on U. So you don't have, but I mean, I'm now dealing with a semi-linear equation, which is relatively simple. You have from the PDE point of view, you have this linear operator, and then you have lower order terms on the right-hand side, and that's only what you have to be concerned with. And in this quasi-linear case, you still solve only linear equations in this local approximation, but you have an extra parameter A, which encodes the diffusivity, and that then in your local description, you also have to change that from point to point. Does that make sense? Does that make sense?
Yeah.
But I mean, I think you want in your local expansion, I think you want to only solve linear equations.
Okay.
Yeah.
Thanks.
Okay, good. Thanks. But I hope otherwise, I hope this general scheme, and I hope in particular the analogy to this first day in this branch rough path, no branches, is clear. Wait, sorry, there was another question in the chat. What is the role of the function gamma compared to rough path theory? That's a very good question. This gamma, if you want, this generalized derivative does not have this is, I think, the only bit in this theory which does not have a direct analog in rough path theory. And one of the main reasons why you never see this in rough path theory is that ultimately in rough path theory, you never have to have a local description in your, I mean, even if you go to higher order and you do branched rough path, your controlled path never has to be controlled to more than one derivative, because the worst noise that you would ever have is the derivative of a function which is just about positive regularity. So it's always, you have to go arbitrarily close to one in your description of the object, but never above one, which is one of the reasons why you never see generalized derivatives. So there is no analogy. I mean, these polynomial dependencies here, and this is actually a really interesting point about rough path, about this theory of regularity structures, because you kind of have the feeling when you look through the proofs and that they shouldn't, I mean, in a sense, they are always determined what this gamma is, and estimates on the gamma are always determined by the bounds that you have from elsewhere. So in a sense, it feels very much like a subordinate quantity. It's a bit similar, like if you have a good control on a function u to whatever, to more than one derivative, you wouldn't normally find it so worrying to get an estimate on its derivative if you already know that the function u is of say of regularity 3/2. But sort of in practice, these derivatives, I mean, so conceptually, it kind of feels like they shouldn't make things more complicated, but in practice, they always do. Well, yeah, but they are there, and they make certainly everything a bit more complicated. Good. So now I hope the scheme is clear. So we have now basically, if you want, defined the analogy of what we call the rough path. So for our stochastic data, we have defined the analogy of what we meant by a model distribution. So the model distribution is actually a modeled function for us. So this function u is what characterizes is that around any base point z, that not, I can well describe it locally by a constant here, and then this increment of the z, and then the this linear function in z with always just base point dependence here. And so this suggests that if I want to have a good description of this product of u of z times eta around the base point, so what I'm just going to do is I'm just going to plug in eta everywhere here, right? So I just multiply everything with eta, everything here in this local expansion. And that is exactly what I'm going to do. The only thing is that for this one, for this product, I've now used this funny, this regularity style notation. And just to stay with it, let me also use regularity style connotation for this term here that we had already discussed yesterday. So I'm going to call it with a pi z x times dot. Why not? Just notation. I am not so sure what that is. Yeah, let me just ignore that. Okay, good. So now I want to do actually spend a bit of time actually just like we did yesterday, actually check that this thing now satisfies this coherence, so this dependence on the base point coefficient. And I think I hope by now this kind of calculation feels familiar to you and you won't be very surprised, but it's still, I think, very nice to check that we've set up things in the correct way and that it just goes through and exactly as it did before. So this is the quantity we want to control. We have again this local description of the product at 2 different base points, and we tested, just evaluated on a ball around this base point. And here I've just plugged in what we have. So this thing here doesn't have a base point dependence, so I can directly compare just the coefficients. And then here, these terms here always do have a base point dependent in the second factor of the description, so the stochastic part, so I cannot put them together immediately. And then I have the same thing here. And this is, of course, something that we had already discussed yesterday, right? If you didn't have this stochastic term in the middle, then the calculation would be exactly identical to what we have done yesterday. Okay, so that's fine. So let's do it. So the first thing, as I had just said, if you just have the terms that I have underlined in green and whatever that color is, so this is as I just showed these 2 terms, right? So this gives you exactly the increment of this generalized derivative times this the distribution here multiplied by the linear polynomial. And then from the change of base point formula, you produce an extra term here, which was exactly this derivative that you needed in this local description here, right? So this was this magic. I mean, I still find it somewhat magic, but of course it is exactly what we did yesterday. So I hope it's not surprising anymore. But let me just remind you that that we got here this improved order bound here automatically because of the smallness of this linear function near the base point, so that this had this improved order bound. And this then compensates exactly the fact, so this has an order bound improved by 1 by this linear polynomial, and this compensates exactly the fact that this generalized derivative doesn't have a bound of order gamma, but only of gamma minus 1. Okay, and so here, of course, you see also immediately why the assumption that gamma is bigger than 1 is exactly what we need. So here we have an order bound of order just below 0. And so if we have a bound here, of a strictly positive order, then this compensates to something positive, which is exactly what we needed in the reconstruction. Okay. And of course, as to be expected, so here this produces already one of the terms that we need in the local description, but of course the extra term with the z is missing, and it's not surprising because it should come from the change of base point formula of the additional term in the germ, right? So that's what we should expect. So let's just check that that is true. So these are the terms with where that come from this extra stochastic term in our local description, and we do exactly the same as before. Very unsurprising. So here we have 2 different kind of point of the coefficient, and we have the base point z here, and we compare it to the coefficient at z bar and here this model also valued at the base point z bar. And then what we do is just we use the change of base point formula here just to replace. Here we use the change of base point formula in this term, and we want to replace this base point dependence by the z bar base point dependence, then in order to allow us to compare it with this. And then here we use this change of base point, which I hope you remember was not really a miraculous thing whatever. And I'm just copying this mu of z here, and I get here this increment of z, which came from this change of base point, and then I multiply it with eta. And you see just this I always find this magic, even though it's kind of not complicated, the calculation that this is exactly what multiplies this, right? So it just gives you exactly the right thing. And this then moves, of course, as expected to the first line of the equation. And then if we put all of this together, you just get, as you should, you get kind of 3 different terms. You get in the first line is the kind of perhaps the most miraculous, where you have exactly, again, the local description of u by the constant as you had, and here this was this term that came from the change of base point in the linear polynomial, and here's the change of base point that came from the stochastic term. And this is again, of course, exactly this modelledness assumption. So that was the first assumption that we had put in our definition of what a model distribution is. And then here, unsurprisingly, we have the increment of this generalized derivative. We have a bound of order gamma -1, as I just said, but here you have this improved order bound just of order minus kappa instead of the -1 minus kappa. So it exactly gives you a bound again, exactly the right order, exactly the same order as the bound here. And then now in this new term we had here, now we use the regularity assumption that we have assumed on this generalized Gubinelli derivative, if you want. And then here we use the order bound that we have postulated for this product. Okay. And at that point, we're done, right? Everything works. We can plug it into this rough path machine, into the reconstruction theorem, and it just works. So what it tells us, this is I've just kind of phrased this now in a theorem, what we get as an output from the reconstruction theorem we just proved. So we let U be a model distribution in the sense of a couple of slides ago, and we're going to define this germ in this language of Caravena-Zambotti, as I said before. So you multiply the base point, you multiply this z expansion, and you multiply this that x thing. And I mean, one thing, so let me just kind of paraphrase. So this now gives us control on the reconstruction, and the reconstruction is, of course, kind of, if you want, this f evaluated on the diagonal, and that can be made rigorous by just approximating it, by just averaging around the base point with epsilon, and then testing against psi, and then letting epsilon go to 0. So that gives you the reconstruction. And so this thing does converge. That was part of the reconstruction theorem to a limit distribution. And this limit distribution is only, of course, as bad. I mean, it's only given by the worst factor, which is this eta. So the distribution itself is only of regularity -1 minus kappa. But we have a very good local description for it, which means this local description, if you compare it to this germ, and around on a ball around of radius lambda around the base point, you get this estimate of order now gamma to the 1 minus 2. So this is really the sum of regularities, right? So the gamma was this generalized derivative irregularity of U, so in the sense of model distribution. And then here you have the irregularity of the eta. So so that gives you that, and then you have to multiply it with all these ingredients. So here's the regularity coefficient of U on the level 0, multiplied by the irregularity of eta, and then here you have the bound for this generalized derivative, for this Gubinelli derivative, multiplied by the order bound, and here you have the bound for the generalized derivative multiplied by the order bound for x times eta. Is this clear, this point? Because I think this is really, I mean, if you've understood this point, you're in pretty good shape already. Okay. So nobody is complaining. That's either a very good or a very bad sign. I'll take it as a very good sign. Okay, good. So now, just as in rough path theory, we have to go and say, well, we have cheated, because what is this thing, right? I mean, this thing is again, I told you in the first before that this, of course, cannot be just constructed by deterministic methods, because right, we were thinking about this product, and I told you already, this has regularity just below 1, this just below -1. So we just about fail to satisfy this compatibility condition, and we cannot give a deterministic bound on that. So we have to go to use probability. So just like in analogy to the iterated integral, where we used Ito calculus, which is essentially just as a covariance calculation. So so we want to do the same thing, right? We want to use a probabilistic argument in an explicit calculation with covariances in order to check that we have the order bound, and that we have, we have an object, and it has to satisfy the order bound, and it has to satisfy the change of base point formula. Okay. Let me perhaps just, I'm already kind of perhaps getting ahead of myself a little bit, but keep in your mind for the calculations that are to come, that this is indeed the only thing I need. This is also something I had already stressed in the calculation in rough path, even, that these axioms that I have to postulate in order for this machinery to work are very flexible. So it's by no means true that there's certainly more than one object that if I have one, I could certainly wait, that's a good question. What comes to that? So I mean, but let's just keep in mind for now that this will be that there will be some flexibility, and that this is the only thing I need. So Simon is asking, how do we know that F solves indeed PAM? Well, I mean, so far I haven't even solved anything, right? I mean, I have just defined a product. I have just said that if I make such an educated guess for what the sigma of U should be and how it locally should look at that point, then I can give a good meaning to the product. I haven't yet even solved the PDE. No. F is just the meaning of the product, right? I mean, but that's of course the hardest point of solving the PDE. Once I have a good discrete understanding of what the product is, the rest is much easier. That's really the hardest point. But I mean, of course, a sensible question that you might ask is, how do you know that this is how do you know that this is actually a meaningful product, right? I mean, that's perhaps sort of the thing that you might ask. But this is, at least as long as we are in the that's something that actually Thierry Boudinot had already asked yesterday also. If I am sort of in the smooth, I mean, okay, if I'm in this irregular setting where I am, then well, okay, that's perhaps a different, but let me just argue on the level of regularization. So if I happen to work on the level of regularization where everything is smooth and pointwise makes sense, then of course we know that this thing here, this F is just is equal to, that's another, F is just equal to F of Z evaluated on the diagonal, right? And so then you see that this term here is just Z minus Z of the base point times eta. And if I evaluate that at Z and here also at Z, then this is just 0. Okay, and then this same thing is true for here because of this polynomial. And this thing then tells us that I will just have the normal product. Okay, so all these extra terms that, at least in the smooth category, that I put into the equation don't change the meaning of what this F is. They don't change the interpretation of what this reconstruction gives me. They just give me better estimates, and they give me I would really view it more as a tool to give me a good commutator estimate, a good estimate on this object, rather than as something. Well, okay, I think for me always the commutator estimate is more of the point than the existence part. Sorry, now I've been rambling perhaps a bit. Does that somewhat answer your question? Okay, you think so. Okay, good. So now let's move on to that. So let me see how am I time-wise. Perhaps actually this is a good point to do the break. So I'll do the break possibly a few minutes earlier, and let's resume in 10 minutes if that's okay. But of course, if you have questions, then so now is break, but you can always ask me questions. Good point. That was a good point. Thanks a lot for pointing that out. Yeah, the problem is that Andres couldn't be here in the last lecture, and he would usually have recorded, but remembering to record and lecturing at the same time is non-trivial and perhaps too much for me. Sorry about that. Okay, good. So anyway, we have this explicit representation of this linear Gaussian object. And so what we now want to do is we want to get a probabilistic bound. I mean, for this, right? So I mean, we want to just multiply this with the regularized noise, right? And for any finite epsilon, of course, this makes sense. But the aim would be to get the right variance estimate that allows us. I mean, okay, I'm not going to talk about passing to the limit. I just want to get a bound for now uniform and epsilon, and I only want to get it on the level of the variance. And you see that you basically want to know that this thing, if you evaluate it on a ball of radius lambda around the base point, then you want to have a bound of the right order. So this would be of lambda to the minus kappa for an arbitrarily small kappa. Okay, so this would be the exact analog of the thing I showed you already for in the case of the iterated integral, right? I did the simple variance calculation with the Ito isometry. And so if we had this estimate, then we have machinery and we're happy. Okay, so at that point it's we're done. So as I told you, it's very analogous to this estimate that you had. So now let's go into this, and this is now really explicit. Okay, so let me show you that. So the one ingredient that we're going to use, and I presume that many of you will be aware of that. So how to calculate moments of Gaussian random variables. I presume you know this. We're only going to use it for fourth moments. So a general fact about if this x1 to x4 is a jointly Gaussian vector, then we can calculate these joint fourth moments just by taking the pairing between the first and the covariance between the first and the second, and the covariance between the third and the fourth. And we have to just sum over all possible ways of pairing them. So I can pair 1 to 3 and 2 to 4. And then I can pair 1 to 4 and 2 to 3. Right? So this is, it's an exact identity. If you have never seen it, you can perhaps believe it to me. And for example, as a special case, if all of these xi are the same, so then you get just 3 times the variance squared, which of course is a formula that I presume many of you will know. I would just assume that you're happy with this because, even if you've never seen it, perhaps you can live with this identity. Well, let's live with it and let's do the calculation. Okay, so it looks like that. So we want to calculate. Let me walk you through this because it looks horrible and I see that. So we want to calculate this the variance of that. That was the aim. And let me just really from the first to this line, I've not done nothing but plugged in. So for here, I have first here this object, eta epsilon. So I've just used the fact that this is the convolution here of this function with the eta. And then I have here's the same. And the only difference is that they are evaluated at different points. So here I have a z0 and here I have this variable z2. And then I want to multiply that with the eta of z2, right? And then I want to integrate all of that thing. So this is just tested here. Okay, so this is just that. So from here, this is nothing but plugging the definitions and this exact convolution identity in. So it's really just an exact identity. And the only thing I've done here is I've just written the second copy of that in exactly the same way with different variables. Okay, so this is exactly the same. The only difference between this line and the next line is that I've put bars over all the variables, which of course changes nothing about the mathematics. Okay, so far so good. And now what I do, I'm just a bit brave, is I just put these integrals outside. So I have these doubled variables and I have now a fourfold integral. And remember that each of them is over 2 spatial dimensions. And I've done nothing but just, so this is now copied here. This thing is copied here. This thing here is copied here. This thing here is copied here, and just I point out to you that all of these are deterministic kernels, so there's no probability whatsoever. So I can pull the expectation through all of that, and then the expectation only acts on the product of these 4 regularized noises. Okay, so this is just here, and then you integrate all of that dz to 2, and now once we have done that, we have to use this Wick's theorem. So this is now a fourth moment of Gaussian. So we have here this with this, which comes here, and then this with here. So this is this first term, and then this with this, and so forth. So this gives the second, and this is the third. So, okay, the 2 messages that I hope you get is A, so far I've not done something complicated, but on the other hand, what I get looks completely horrible, and you really don't want to work with that. So I hope you agree with that. And this is particularly true given that this is sort of the simplest example of any of these computations that you will ever want to do. If you look at more complicated equations, you will have to look at things that are of 6th, 8th, whatever order in the Gaussian noise, and these integrals just start to look that you really, really, really don't want to work with them. So it's you have to at least develop some formalism that allows you to kind of keep track of what's actually going on, because this clearly looks horrible. I mean, you may be able to work with this. I wouldn't be. So let's do this. Let's do this with graphs. And I actually like to take a bit of time to motivate you to that graphs are cool. So okay, this starts to look messy. So I hope you were convinced in that. And again, I had already made the point that this is really the easiest possible calculation of this type that you will encounter. So we need a better notation. Okay, so let's do this here. And I've done this here. So here we have this. I've just kind of written a schematic graph that keeps track of all the information for the integral that we need. So we have this noise here, which is represented by this blue dot here, and I have this noise here, which is represented by this blue dot here. So this is I've written the variables. So this is integration variable z1 and integration variable z2. And now here, the fact that you have to integrate out, I mean that you have a kernel that connects these 2 points here. This is the G here in this line, and the fact that you have to integrate it out with dz1. So that's sort of this whole bit of the graph. And then you have this other noise here that's down here. So the blue dot is always noise. And then you have this against this regularizing kernel. So that goes here. It's this green kernel at the bottom. And here you have the variable z0. Okay. And so then you have the second thing, which came from this counter term, this positive renormalization term. That's the same, except that if you see that this kernel now connects not these points, but actually connects these points. And you can actually introduce a single shorthand notation for that, where you draw a bar through that in order to say that you have to take a difference. And I mean, I don't know, I find this graph looks prettier than this horrible integral, and it captures it's just a very compressed way of capturing the information in this integral. Okay, it's really just a notation, but it's very convenient to work with, especially if you go to more complicated graphs. So that's good. So now, this was just for the integrals in themselves. Now you have to do the squaring and doing the pairings and everything, but that's now relatively simple. So this Wick's theorem now takes this that we have seen now takes this form. So you just if you want to calculate the expectation of this thing squared, you just have to double the number of double the copies. So you have one copy up here and you have one copy up here, which is exactly what I did on this messy slide. And then you have to decide what you want to pair. So the first one you pair here and here. And then you have to pair one's cross across here. That's the second term. And then you have to pair the third pairing is where you have to pair these things. And there you see that that actually gives you a square, because if you do the pairing up here and you do the pairing up here, it just gives you the identical term. So you just have to have a single graph, a simpler graph, which you just square. That's I mean, I hope this is, I hope you agree that this is looking nicer and perhaps a bit more, I mean, easy to trace mistakes also in these graphical things than if you write these horribly long formulas where you easily lose the names of variables somewhere. What is integrated against what is important in this calculation. And I mean, let me also just make a remark, kind of comparing to the literature. Of course, the idea of representing these very complicated generalized convolutions where you have multiple convolutions over many variables all against each other to represent them by graphs is, of course, really not new. So this is something that if you look at, say, perturbative QFT, that's what Feynman diagrams are. So this is really not a new idea. This has been around for 70 years or so. All right. So now that's good. So now I've just used it to introduce a different notation. I've not solved any problem, but no problem. Let's move on. So the first thing is a nice simplification. Now, when I analyze this, I use this version of the Cauchy-Schwarz inequality. If you have, that's a general fact that you can always, I mean, this is just Cauchy-Schwarz. If you have a function of 2 variables and you have kind of this cross term where you have, I mean, this type of scalar product, you can always just by Cauchy-Schwarz bound it by the same thing, by the diagonal thing squared. And that allows you actually to say that the second graph is bounded by the first graph. And so we can forget about the second one and we only need to do the first and the third. So that has already reduced the complexity of our problem by a bit. And so now let me do the first one, which is sort of the main one. So for simplicity, I'm now going to ignore the environment. Here you have these correlations of the regularized noise, and this is an approximate delta function. But I'm just going to do the calculation, the limit now, where I set epsilon equal to 0. And I mean, you can do the approximation thing, but let me not do that. So in this case, you now have to, I mean, right, you just link those things. I've just merged them, and so this gives you rise to this integral. Okay. And now here, I mean, now it's analysis. I will not walk you through the details of this, but it's not very complicated. You can actually check. I mean, these are all exercises, so actually I don't want to do them. So you will see that it works. It gives you the estimate that you wanted, okay? And so I leave it as an exercise for you to check that this is all true. I've basically given you the hints of what you have to do on the way. And another exercise here is to do the same kind of analysis for the one-dimensional, so the 1 + 1 dimensional space-time white noise, where the same calculation will work, but you will get a bound here of order -2, which corresponds to this lower regularity situation. Okay. So good so far. Okay, so that's looking very promising. So that looks like it gives us hope that we can actually implement our program of calculating this z and then go on and solving the equation. So it's just this graph 3 left, right? So that shouldn't be so bad. This was just a square of something, so that looked better. So let's have a look at that. So this was here. I'm going to undo, when I analyze this thing, I'm going to undo this line again. So I'm going to remember that this was the difference of 2 graphs, one connected to here and one connected to the origin. And I will also leave it as an exercise for you that this B graph, the second thing, does what it should, okay? So we're not going to worry about that one. But let's have a look at this A graph, what it actually means. So here I've kept track of the delta epsilon for now. So this is, if you translate it back, is nothing but here you have an integral of this elliptic Green's function in 2 dimension, and you average it on a ball of radius epsilon around the origin. Okay, so this is what this integral does, and then after you take averages. Okay, but this is actually a constant, right? Because this doesn't depend on Z2 anymore. Everything is translation invariant. And so you basically just average a constant. Well, okay, then you can forget about the averaging as well. So this is just a constant, the whole thing. And what is this constant? This constant is the average of a Green's function over an epsilon ball around the origin. And that's really bad news, because the average I mean, the average of course blows up. It blows up like log epsilon, right? So this is sort of at the end of our analysis. It hit us so that we were, I mean, perhaps everything was in vain, because the thing we wanted to do actually diverges. So I mean, I think our ansatz was quite sensible. We regularized things. Our main term did what it should do. We did this complicated analysis, well, sort of complicated analysis of these integrals, and that looked all very promising. Now, sort of the last step, it hit us that, well, we just encountered this divergent constant. That's bad news, right? So the conclusion is the thing we did just doesn't work. So it just diverges as epsilon goes to 0. And well, what can we do? But I mean, I've learned recently this saying: we have come too far to only come this far. So what do we do? Well, let's just throw the term we don't like away. Okay, so we're just going to do a new definition, is where we just subtract the term we didn't like. Okay, so this counter term here is exactly what we didn't like. That's exactly the divergent term. And what we have just proved is, if we do this, what is called renormalization, then it actually converges. Okay, so that was what we have proved with all of this calculation is this: we have gotten the order bound, and the change of base point is not hard to check for this thing if we subtract a constant which diverges as epsilon goes to 0. Okay, so the theorem that, well, we haven't quite proved that, but that's the theorem which is true, is that there exists a random distribution, which I will denote by, well, this weak product if you want. such that these renormalized products, so I have to subtract a constant, converge to it in a sense that, actually in a pretty strong sense, is the sense of stochastic moments of all order measured in these norms of just below kappa. And furthermore, you have the order bound that if you compare this thing with well, the order bound that you want, and let me just kind of perhaps in terms of it's quite striking that this counter term is you have done a renormalization in this term, but you have absolutely not changed the recentering, not at all. You have just changed the definition of this thing, but still you have the order bound. That was the outcome of the calculation that we have just done. Is there a question on this? Because I've been going pretty fast in the last minutes. Okay. And this is either a bad or a very good sign. So what we have done now is we have done a completely unjustified thing, which is this thing we have asked a question and we have figured out that we didn't like the answer, which is the thing we wanted to converge doesn't converge. So we have just changed the question in order to get an answer that we like a bit better. Okay, fine. Let me perhaps just in the proof of this theorem mention a few words that just like what we had done, what we had already kind of implicitly mentioned a couple of times, and also Milton mentioned this in his lecture before, is that this passes through some Kolmogorov type theorem, and just as before, just as like actually in the case for Brownian motion, where if you want to prove Hölder regularity, you also have to do the same thing, where you need to know that if you want to control pth moments of something, then you can control them by the second moments. That actually also has a somewhat similar flavor to what Julian's partially explained with his concentration inequalities. And this is true for Gaussian polynomials. So this is a property that we use, and this goes here under the name either Nelson estimate or hyperconductivity or Wiener chaos. So those are kind of the keywords that go around. And that is what is used in the post-processing. So once you have this variance bound that I have showed you how to get, then you use this kind of heavy machinery to get to the theorem that I just stated. And the other remark that I've already, I think, also stressed a number of times is that this distribution that we had here is, of course, globally an object only of regularity minus kappa. But again, we have this better control of it when we tell that the centered version actually has an order bound of order minus 2 kappa. And that's really, really crucial in this whole theory. And again, very similar, I'm repeating myself a bit, but it's such an important point that with this, by recentering things, we actually get better control on the small scales. We get better estimates than just the global regularity. So this looking at things around base points is extremely important to get the right estimates. Okay. Okay, so that's sort of good news. So what this tells us is now we can of course plug this into our machinery, into the reconstruction theorem, and we can give a meaning to this product u times eta, right, or sigma of u times eta, whatever you want. Let me just do u times eta, and it gives us something. But now we have to think for a moment what actually the object is that we get. I mean, is it actually something? I mean, the reconstruction theorem tells us that something exists, but what is it actually? I mean, what is it that we have? And I told you, let's do this on the level of the regularization. So here we have the classical product, right? So that's fine. But I mean, the reconstruction is just the germ, if you want, on the diagonal. So here we have the classical product. That's fine. Here in the last term, this doesn't change the value of the reconstruction. It's needed to prove convergence, but it doesn't change the value, right? That's because this is 0 here on the diagonal. And here, so let me just remind you of what this was. So this is on the, or when it's actually written here. So here you have this product here evaluated at Z, and then here the recentering, and that was the thing that canceled before. So that we had seen, I mean, that was in this naive, where I told you also yesterday to Thierry that this hasn't changed actually the value of our product by doing this, because these things cancel each other. but the presence of this extra constant destroys this property. So this actually produces an extra term. Okay, so if I choose now to define my germ on with this renormalized product as opposed to the classical product, if you want, on this epsilon, it gives the product a different meaning. So if you want, the renormalization that I have done on the level of this product z times the eta translates immediately to a renormalization that I have to do here on the level of this product. Okay, so does this make sense? I had to add an infinite term on the level of this product with the eta times the z, and the z is used in the local description of the u. And so now, hence, if I want to multiply u with this, then I need to then I get also a constant, but it's controlled, and I understand how it changes things. Okay, it's kind of the bad news is I have to change it by a divergent constant, but the good news is I understand very well how that constant looks. Okay. And now let's be a little bit more concrete actually on the next slide. So this is for an abstract model distribution, but we actually know in the concrete case where we solve the PAM equation what this Gubinelli derivative actually is, because in this case here, so the Gubinelli derivative is just going to be here the sigma times sigma prime, right? So what we are going to get is really looks like an Ito-Stratonowicz correction. So we need to, if we take a regularization if we work on the level of regularization, so we work with a regularized noise here, what we have to do in order to pass to the limit where we remove the regularization is to put these counter terms, which are, which really looks like an infinite Ito-Stratonowicz correction. Okay. So I'm conscious of the fact that I've been pretty fast again. So if you stop me and ask a question here, I think that would be good. Is this sort of clear, or is it Friday evening and much too late anyway?
So in basic words, so this is also comparable to what we did in the rough path when we just added on the second level object this constant t minus s, just without all the fancy diagrams.
Absolutely, it's exactly the same. I mean, of course, also the fancy diagrams were just notation. They don't change very much about the content, right? Yeah. I mean, the only difference, perhaps conceptually, is that the constant actually diverges. So I have to do kind of an infinite correction to even make it converge.
Okay.
That's not present in rough path theory. But in a sense, it's funny because in rough path theory, there could also be a divergence. It's sort of due to a forward-backward symmetry in time that you don't do it. So you could actually easily construct two Brownian motions that if you wanted to integrate one against the other, you actually also have a log divergence. It's just not the thing that you encounter in solving SDEs. So even for if you wanted to do rough integration, you could create examples where you would need to do such a renormalization. It's just not what appears when you solve ODEs. But yeah, but I agree. Yeah, I mean, this was sort of my intention to make it look as similar as possible to that. So thanks for spotting that. Okay. Good. So there are two more points I want to make before concluding this lecture. So one is now to convince you that this thing that we have done, I mean, it feels really very much like cheating, doesn't it? So we have basically figured out that oh, sorry, actually, before I go to that, sorry, I wanted to just conclude before I come to these last 2 points. So there's 2 more slides. So this is just a summary sort of I mean, I've of course shown you more the main ideas, and now I want to just in a few words kind of wrap up and give you an overview of how you now wrap up the argument, the existence and uniqueness theorem for this equation, and what you can actually get. So what you can actually now get with this machinery, I have now told you how you can even interpret this thing. So with this infinite product, and so what can now be achieved with this method, or that was actually the main result in this context, of Haira's original paper on regularity structures was that he used this idea, these model distributions, to prove existence and uniqueness up to some small random time t. And the way it's done, you also get stability of the solutions in the data. And in particular, what this method then allows you to prove is that indeed, if you do these approximations where you do this, where you do the epsilon approximations, you do converge to the limit here. And how you do that is really you fix your model, and then you do deterministic analysis and solve this as a fixed point problem in a suitable functional space. And sort of the striking idea is that this functional space is a space of model distribution. In particular, the space actually depends on the realization of the model. But again, this is actually very much reminiscent of what happens in rough path theory, where you also, in your existence and uniqueness theorem, or if you want in Lines universal limit theorem, you solve a fixed point problem also in a space of controlled path. Well, that's more Gobinelli's formulation, but that's what you do. And I've sort of actually shown you, I think, conceptually the hardest part. There's one other kind of hard PDE estimate that is missing in order to complete that program, and I haven't discussed it at all. So let me at least admit that there's one more ingredient, one really hard ingredient missing, which is a Schauder estimate, which essentially tells, because if you want to do a fixed point argument, you sort of start with knowing that you have a good description of U, and I've now told you how you can use this to postulate a good description for the sigma of U times eta, and then how you can then reconstruct that. And then you have a good, then you have an object, and you have a good local description of it out of the reconstruction theorem. But then if you want to do a fixed point problem, you have to go back. So you have to say that now that I know this object and I know what it's described by locally, I also need to then go back and need to know that U, that again, I have a good local description of U. And that is, I mean, possible. It's a core part of the theory, but I won't have time to discuss it. So I just want to mention you that there's another analytic type estimate missing that I won't go into. And let me also perhaps stress that by just doing this, there's actually a limitation. If you just do the program this far, you get these nice stability results, but it's limited to a short time existence and uniqueness. Which is sort of inherent, right? It's actually almost reminiscent of when you prove for ODEs that you have local existence and uniqueness for locally Felder vector, for locally Lipschitz vector fields. Then you do this also with a Picard iteration, and this argument has very much the same flavor. So if you want to do more than local existence, you need more arguments than just what I showed you. Okay. And also, I mean, in practical terms, that's possibly not so obvious from what I showed you, but in practice, these things also really only works for finite volume without extra work. Okay, so right, so now I come back to what I actually wanted to still say. So these two things. So the first point that I want to still make, I want to argue that this renormalization is natural and that it gives you the correct option, right? Because so far it's the correct object. Because so far it perhaps seemed a lot like I was cheating. So I have just, I mean, I've done a natural approximation. It didn't converge, or I mean, I didn't know how to prove it converges. So I have just replaced it by something else. And for the something else, I have shown it converges. So that hardly seems like a satisfactory answer to the problem. But let me now make an argument that this renormalization is actually something sensible that gives you the meaningful answer and that gives you the meaningful model. It's the correct object to work with. And I want to argue that, but not on the case of the stochastic heat equation, but I actually want to argue on the level of the KPZ equation, where you have to do something very similar. But I mean, the stochastic heat equation is, of course, closely, the KPZ equation is, of course, closely linked to the stochastic heat equation by this Cole-Hopps transform, okay? And that I want to just explore for a few minutes now. So we had seen the KPZ equation, okay? And actually before the theory of regularity structures was around, actually there was already a well-established notion of solution for this thing. And this was actually just through this Cole-Hopps transform, right? And I had told you very briefly on the first slide that if you take a solution, that if you kind of at least formally take the KPZ equation, take this KPZ equation and you exponentiate it in this way, then the function u that you get actually solves this multiplicative stochastic heat equation. So this is now an equation with extremely similar structure to what I had before. The only difference is that now you have your space-time white noise, and the sigma of u is a u. Okay, so I hope it resembles what we've done. It's not what we discussed, but it's a slightly more complicated example of a very similar type. And so the pragmatic approach that was taken in the literature, and actually up to today is very often taken in the literature, is to just take this red box, the stochastic heat equation, as the definition of the KPZ equation. And that does simplify the problem in a certain sense, because I told you that this equation with space-time white noise, solving it with regularity structures is actually not much easier than solving the KPZ equation, but this is actually sort of the prime example that is within the reach of what can be done with classical SPDE methods. So here you just use the classical D'Aprato subject type analysis and you can solve it. And then you can also prove that something you have to prove, that if you solve this equation, then actually solutions are non-negative. Well, if you start with a non-negative initial datum, then they're actually strictly positive for all times. That's something you have to prove. But then once you have that, you can undo this transformation by just taking the logarithm, and you have a solution for the KPZ equation, right? And then you have an object that you can work with. So that's sort of the pragmatic approach to this equation. If you don't want to worry so much about this renormalization business, and I want to actually give you the proof of this, right? So I have the solves here. So let me tell you why this is true. Okay, let me show you the calculation. So here's the calculation. So I prove now that this solves the multiplicative stochastic heat equation. Well, that's not so complicated, right? So let's get dtu. I use the chain rule. I get a -1/2 u dth. I do the second derivative. So then once both derivatives hit the h, so I get this term out here, and then once I have the exp, and then hit the exp again, so then I get this here with a dxh squared. And if it was too quick, you can do the calculation. It's not hard, and then you just subtract them, and then you get this thing, but this solves the KPZ equation, so xi, so you're done. What? So this seems pretty sensible as a calculation, and of course, I mean, in the smooth regime, of course, this transformation, how you go from a Hamilton-Jacobi equation of this type to the heat equation is, of course, very classical. So this is not this calculation is by no means new, of course. But if you now think about it a little bit harder, you realize that this is cheating, because you know already that these xi's are very irregular objects, and probably the chain rule is a bit unjustified. You know that at least for Ito calculus, you have to deal with you have to use Ito's formula and not Ito calculus. So this seems a bit of a brave thing to do. Let's do this a little bit more carefully, this approximation. So what one can do if we do it with Ito calculus is one can just regularize in space, right? That's honest. I can do that. And so then you have this KPZ equation here, and now takes this form that I have written here. And now I have here kind of something with a dw, and the epsilon means that it's smooth in space, but this is still wide in time. So I have to do Ito calculus, okay? And now I do the same calculation. So I do the same thing, and I calculate now instead of taking the time derivative, I take this Ito differential, right? And you get exactly as you wanted to. You get the term that you had before, sort of the u times the Ito derivative of this one. But as you have Ito formula, you have an extra term, and this is just if you want this, it's just a quarter times u times the quadratic variation of this dw, and this is just this is just the covariance matrix. If you want the covariance operator evaluated on the diagonal, and this is an approximate delta, so this actually diverges like 1/epsilon. Okay, so this thing actually diverges. So if you did this calculation like that, then you would come up with here this stochastic heat equation with this extra term. Okay, and Now this, if you plug this into, I mean, the kind of the classical SPDE work by Alada Prato subject or so tells you that this thing without the constant converges. So putting a constant here is probably not a good idea. And let me also just as a kind of as a side note, just stress that this is again exactly an Ito-Shatonovich correction. If you had a general sigma here, this I mean this is the equation here with sigma equal to the identity. So this is exactly sigma prime times sigma. Okay, perhaps with a half or okay. So now this is not a good idea. But okay, so if this doesn't converge, we have to perhaps change something in the original regularization. So let's just change the definition of this thing here in order to make this term disappear, and that one can do. So if you just take a look at this approximation here, where you have now done this, put this infinite constant in the approximate KPZ equation, you recover the heat equation without the extra term, and for the heat equation without the extra term, you know it converges to the object that you like. So hence, this also converges to the Kohl-Hopf solution of the Kohl-Hopf KPZ equation, right? Sorry. This thing doesn't converge, so you have to change the definition of H. So this thing then makes this term disappear, and then this thing without the term disappear converges. So this thing also converges. Okay. So even if you perhaps didn't make this so explicit by working with the Kohl-Hopf solution of the KPZ, you have all along actually done a renormalization. You just didn't have to make it so explicit, but it was there. And it's, I mean, this is just one example where you can justify in this way that the renormalization just has to be there. And there are a number of other ways where you can justify that this is the correct object, but for example, by deriving them a scaling limit of interacting particle systems or so. So these are just the physical solutions, and one has to live with the fact that there's infinite constants, there's a renormalization. Okay. Was this going very fast, or is this still okay? Okay, so then the very last point I want to make in these lectures here is about the scope of this whole methodology. Okay, so I've now shown you that this works for the simplest example, the PAM. The 2D PAM is the easiest equation that can be dealt with in this framework, and you might ask yourself sort of what's the range of problems that can be treated. And that can actually be kind of narrowed down pretty explicitly. And there's this key condition which is called subcriticality in this business that kind of tells you that you have a chance of using this theory. And so subcriticality is the question of when does all of this machinery have a chance to work. And sort of as a meta description of what this condition means is that on the small scales, where I mean this problem really, this whole theory is geared to treat the small scale behavior of solution. And what we want to, because I mean this is inherently a perturbative approach, right? So we want to build a local perturbative expansion of our solution based on the Gaussian noise and polynomials in the Gaussian noise. So the kind of philosophically, it doesn't seem so strange that we want the noise to be the dominant term on small scales. And that's the condition that we need to satisfy to even start with this whole analysis. And let me, I mean, this is perhaps too philosophical. Let me make that very explicit how you would check that. So for example, and just with some power counting. So what it just means is basically the noise term has to be the most irregular term on the right-hand side. And for example, if you want to do this for PAM or stochastic heat equation, so I've just rewritten the equation and I've just written it with this freezing of coefficients thing. So this sort of corresponds to the noise term, and here's the perturbation. This should be a perturbation of the noise. And what we want always is that the perturbation should on small scale be better than the noise. And let's just do the power counting. So here, the worst term here is of order, this is of order regularity -1. So we have argued power counting, you gain 2. So you go to +1 on the right-hand side. And then you gain this extra 1 here, multiplying with 1, that should give you a 0. So that's good, right? So this means this object on small scales will be much smaller than that, so that this is the dominant thing. So we have a chance, so it's good. And that's, of course, what I just showed you, that it indeed works. Now let's go to the three-dimensional case of PAM, which in terms of power counting is equivalent to the one-dimensional case of space-time white noise. And then it's still good, right? Because you have a -3½ here. You go, you gain two derivatives, you go to +½ and then you see you have here, this gives you you gain kind of a smallness of degree +½ and multiply it. So this is still bigger. On small scale, this is still smaller than that. So I mean, the exponent is bigger, so the thing is smaller. So that's looking good also. So this will work. But indeed, you will have to go much further in the expansion. So in the case that I showed you, I've only added a single extra stochastic term. And by doing this, I think you have to go 2 levels further. So you have to add a lot of extra stochastic terms, and you have to add also a lot more diagrams, do a lot more stochastic computations, but it works. And in the case of PAM in 4 dimensions, or stochastic heat equation in 2 dimensions, which is equivalent again, you would have a -2 here, then you gain 2, so you go to 0, and then here you see you don't gain anything anymore. So this is going to be what is called a critical equation, and this doesn't work anymore. So for critical equations, regularity structure doesn't work at all. And okay, so basically we do have a theory for these equations using regularity structures in these 2 regimes, but we don't here. Let's do this for this exercise for another equation for fun. Let's do it for 5-4, which is another one of these very prominent examples. So there we have here just the noise, which should be the most irregular object, and let's do it in 2 dimensions. So this has regularity -2, space-time white noise. So we have 4 effective dimensions. 4/2 is -2. You go to 0 with a heat operator, and so then you cube it, and cubing something of the regularity 0 gives you in this power counting way a 0. 0 is bigger than -2, so this looks good. Let's do it in 3 dimensions. So in 3 dimensions, we have -5½ here. You go to -½ and then cubing of distributions has here the property of adding these numbers. So this gives you a -3½ but -3½ is still better than -5½. So this is good. And let's go to 4 dimensions. In 4 dimensions, it stops working. So you have here a -3. You go with the heat operator to -1. Then you multiply by 3, and you see you again. Sorry, this should be a -3, of course. So you see you are again critical, and again regularity structures doesn't work. And here this is actually this is actually not just a failure of our method. This is actually something, at least on the level of the equilibrium measure, with completely different methods that has been analyzed, and there are these triviality results that tell you that if you take reasonable approximation of the measure, it's just you won't get something interesting. So this is in dimension higher than 4. This is a classical theorem, and in a 4 dimension, it's been a conjecture for a long time. It was only finally resolved about 2 years ago. And as an exercise, I leave for you to just check that the KPZ equation with the same kind of power counting is subcritical for any dimension less than 2, and becomes critical in 2 dimension. And that will actually be discussed in one of the lectures next week. I've seen that Giuseppe Cannizzaro is going to present work on what can be done actually for critical KPZ equations, and possibly Nikos Tsigoras will as well. Okay. So that's the scope of where we can hope to do something. And let me just perhaps finally kind of tell you the scope of this. I mean, Martin and his group have indeed actually developed the theory to quite a remarkable degree. So there was the original paper in Invenciones that led to him winning the Fields Medal, and this contained. I might want to claim that up to this integration, this Schauder regularity estimate that I did not present, I think I have explained a number of key ideas of this paper, sort of. And there are these 3 really substantial follow-on papers. I'm not saying I've done everything, but sort of I would still argue I've explained sort of some of the key ideas of this. Sort of all of this extra machinery is then built to systematize this theory and to make it work automatically for equations where the expansion can go up of arbitrary order, right? I mean, you see, you have the subcriticality threshold, And in principle, this local expansion theory works all the way to the threshold, well, except for the not excluding the threshold, but everything up to the threshold. But the closer you go, the more terms you get in your expansion. And also the more complicated these algebraic miracles that, I mean, all these cancellations become. And so this group has really spent, I mean, quite remarkable efforts of developing the algebra that goes into this, all of this systematically. And so this is now understood to quite an astonishing degree. So I mean, this paper here, there's a very general algebraic framework where is developed that that makes these calculations that I've shown you by hand, that makes them all automatic. This paper also quite remarkably does the stochastic calculations that I've only hinted at a little bit today in the lecture. So all these analysis with the graphs on these integrals also tells you that these work automatically in a huge generality of situations. And then this is sort of a catch-up, final conclusion of all this work, where in particular the issue of renormalization is treated, where kind of it's shown on great generality that if you have to put infinite constants here, then it gives you something sensible on the level of the equation. That's this thing that I also showed you in the special case, that putting a constant on the level of this quadratic polynomial in the noise, then if you put it in the equation in the right way, it gives you also something sensible on the level of the equation. So this is, I mean, this is quite remarkable, quite developed. I must also admit that reading all of this is quite a time commitment. So I've done the arithmetic for you. That's a total of 561 pages. So it takes a while to read everything. All right. So I think that's it. I only have some more references, and otherwise I would stop here unless you have more questions.
Let us thank the speaker.
Thank you. That's actually a question that I would like to answer. Is there a singular SPDE without the need for renormalization? Yes, absolutely. That's a very good question. There is. I mean, yes. I mean, in a sense, that's an interesting question. So yes, the answer is yes, and in a sense, it's the atypical thing. So power counting would typically suggest that there are certain diagrams with certain integrals that have power counting have the ability to have the possibility to diverge, and then by default they would diverge. But there are situations where there are additional symmetries in your equation, and even though, I mean, you have something that in terms of absolute value could diverge, but there's a cancellation which just cancels that out and makes it equal to 0. And I mean, in a sense, a very easy example is, of course, if you do the stochastic heat equation, like the Prato-subject theory, if you want, that I just told you, plus sigma of u, and you do a regularization only in space, okay? And then you can prove that as epsilon goes to 0, that you converge to the, I mean, this is what people have done for 20 years or for 30 years, that this is exactly what this martingale-based SDE theory of SPDEs was able to do, to prove that these things, as you remove the spatial regularization, converges to the Ito solution of this thing. But so in a sense, there is no renormalization in the stochastic heat equation, but that fails to be true if you take a space-time regularization. So if you do what is done in this Wang-Sakai theorem, for example, so I mean, if you regularize in space and time and want to remove that regularization, then you will find that you actually do have to subtract counter terms and in order to get to the same limit. And that was actually worked out also in one of the very first papers on regularity structures by Martin and Etienne Pardou. And there are more sophisticated examples where sort of by magic, infinite constants that should be there just disappear. In a sense, it also happens in the KPZ equation, where if you do the analysis, you have kind of a number of trees and you have this principal divergence with the 1 over epsilon that we have just discussed. But then there are actually some extra divergences in some higher up the diagrams, which are only logarithmic, but they actually cancel out. So you don't see it in the final equation, but they are there in the trees. Does that answer the question? Okay, excellent. So if there are no further questions, I think that's it. No, so thanks a lot for sticking with me to the end. And of course, I'm looking forward to seeing you back next week for the workshop. I think it's going to be exciting. And so thank you very much. And I'll just stop here.